I'm Diana Burden, and I'm majoring in bioengineering. I plan to become an orthopedic surgeon. They treat all kinds of ailments to the bones, joints, ligaments, and tendons. They can have a variety of causes, which include diseases and injuries like fractures or arthritis or osteoporosis. The work that orthopedic surgeons do ranges from setting complicated fractures to fitting prosthetics to designing new implants, especially for joint replacements. Some of them are completely and entirely do research and work a lot with other engineering fields, and others are completely devoted to patient care and doing things such as surgery and just normal day-to-day medical practice. But there's many who are in the middle who do patient care and medical practice, and that's what I'm most interested in. It's really beneficial to researchers to have doctors that usually have an engineering background and practice medicine as well as conduct research, because they have better insight to how the doctors will use medical devices and what ease, especially since these have to be implanted, that how difficult that would be in practice rather than just in theory. But anytime that the doctors and engineers design new medical devices, they have to use material science concepts to decide the material composition of the device. They face the normal engineering problems of strength and hardness and ductility and wear and electroconductivity, but also when designing medical devices, there's an added problem of biocompatibility, which is one metal that was found in the 1950s to be surprisingly compatible and be pretty bioinert is titanium. In an article called Titanium Alloys for Hip Joint Replacements, Dr. Schmelitz said that titanium pretty much only became popular because it did not elicit as negative of a reaction from the patients as other metals that were more mechanically sound. But even now, most joint replacements still use titanium, but now they use titanium alloys rather than pure titanium as they did in the 1950s. For total hip replacements, the goal is to have them function as close to actual bone and cartilage as possible. And for most total replacements, they have a femoral head, which is this right here, and it's connected to the femoral stem and neck, and this would all be made out of titanium. And then that connects. This is a casing that stops wear, and that's usually made out of a ultra high molecular weight polyethylene. And then this is called the acetabular cup, and that's connected to the pelvis, whereas this is connected to the rest of the femur, and this is just setting in between the two to stop wear. And these for titanium, the type of titanium that's usually used in medical devices is it's called titanium 6 aluminum 4 palladium. So that's titanium 4B. That's the most common titanium alloy, especially in biomedical applications. This has an elastic modulus of 114 gigapascals and a tensile strength of 976 megapascals, a yield strength of 847 megapascals, an elongation percentage of 5.1. And with that information, we're going to determine what the maximum load with a safety factor of 2 that can be placed on the titanium hip with a diameter of 28 millimeters. And we assume that the load is evenly spread across the head surface. So we have that percent elongation equals delta L divided by LO times 100, and then strain equals delta L delta just LO. So we have that strain and percent elongation are essentially the same, except percent elongation is multiplied by 100 and strain is not. And then next one, stress equals the elastic modulus times the strain, and then the stress also equals the force over the initial area. And because this is a semicircle or a hemisphere, the surface area is going to equal 2 pi diameter divided by 2 squared. And the safety factor is 2, which means that the ultimate stress divided by the actual stress has to be 2. So this is all of the formulas that we will be using for this problem. We have percent elongation, and then strain, and then stress equals elastic modulus times the strain, and then stress equals the force over the area, and then what area is, and then the safety factor. So then we'll plug all these in. We'll end up getting that we'll derive that the safety factor also equals force divided by, or ultimate force divided by actual force. So to get our actual force, we'll end up having the percent elongation divided by 100 times the elastic modulus times 2 pi diameter divided by 2 squared, all of that divided by the safety factor. So this will ultimately get us to our final answer. And we plug in all the values for these, we get so this is the ultimate to get the actual force that the head can support. And that's going to end up being and the force is going to be 3.58 times 10 to the 6 newtons. So obviously that no person would ever put that much force on their hip, but there's other factors that we'll go consider, but we just want to make sure that the force will be able to support, the hip will be able to support any force that a person can put on it. In order to find more information out about how orthopedics and biomedical research and material science relate, there are articles. There's one called Mechanical Properties of Biomedical Titanium Alloys, which is found in the Journal of Material Science Engineering. Another one that is called Titanium Alloys for Hip Joint Replacements, that is found in the Clinical Materials 2.1 journal. Another one found called the Ideal Femoral Head Size and Total Hip Arthroplasty Balances Stability and Volumetric Wear, which is found in the HSS journal. And another one, which is the Assessment of a Fictitious Domain Method for Patient-Specific Biomedical Modeling of Press-Fit Orthopedic Implantation, which is found in the International Journal for Numerical Methods Engineering. And finally, there is titanium alloys for biomedical applications, which is found in Material Science and Engineering journal as well. That's all.